Hey guys, welcome. Today, we are completely tossing out that boring textbook. Instead, we're going to hack Chapter 3 and help you master metals and nonmetals in under 10 minutes. If you're prepping for exams and get bored easily, this explainer is literally made exactly for you. All right, let's dive right in. Okay, imagine this. A metal that's so incredibly soft, you can just slice it with a butter knife. Or get this, a metal that violently catches fire the literal second it touches water. Sounds totally made up, right? Like science fiction. But here's the interesting part. These wild, mind-bending exceptions are the exact things examiners absolutely love to test. You see, science exams don't just care about the rules. They really want to test if you know the rule breakers. Which brings us to Section 1, the rules and the rebels. Now, we've got to quickly establish the normal physical rules of elements before we can jump into the fun stuff, the rebels that break them. Usually, normal metals are lustrous. They have a nice shiny surface, they're hard, and they have these amazing superpowers called malleability and ductility. That basically means you can smash them into super thin sheets or pull them into really long wires. Gold and silver, they are the absolute, undisputed champions of this. On the flip side, normal nonmetals are dull and brittle. They'll shatter easily. Think of a lump of coal, and they are frankly terrible conductors of heat and electricity. But why does this happen? Well, it's just their standard physical nature. But now let's look at the metal rebels. We're going to rapid fire through these exceptions because, trust me, these rebels are absolute exam gold. First up, mercury. While literally every other metal is solid at room temperature, mercury is just chilling as a liquid. Then we have gallium and cesium. Metals are supposed to have super high melting points, but these two, they will literally melt into a puddle right in the palm of your hand just from your body heat. Crazy, right? And finally, the alkali metals, lithium, sodium, and potassium. Forget being hard and tough. These are so soft you can literally just chop them up with a kitchen knife. And hey, the nonmetals have their own rebels too. Take iodine. It's a nonmetal, but surprisingly, it's actually shiny and lustrous. Then there's carbon, which is famous for taking on these wild different forms called allotropes. Diamond is pure carbon, right? It's a nonmetal, yet it is the single hardest natural substance on the entire planet. And graphite, the stuff inside your pencils, is another form of carbon, but it completely breaks the rules by being an excellent conductor of electricity. Examiners love these exceptions, guys, so lock them into your memory for sure. Moving right along to Section 2, the chemical battlefield. Now we're shifting from what these elements look like to how they actually fight and react with each other. Normally, when metals react with oxygen, they form basic oxides. But we've got some double agents on this battlefield known as amphoteric oxides. Aluminum oxide and zinc oxide are the classic examples here. These two literally play for both teams. They can react with acids and they can react with bases to produce salt and water. They just seamlessly adapt to whatever they are fighting against. All right, here is a massive, highly tested exam question. Why are sodium and potassium kept completely submerged in kerosene oil? Seriously, take a second and think about it. Well, the answer ties directly right into our metals versus water showdown. Sodium and potassium are so incredibly aggressively reactive that if you just leave them out in the open air or drop them in cold water, they react so violently that the hydrogen gas they produce catches fire instantly. That is exactly why we have to lock them away in kerosene. Now step down a level to calcium and magnesium. The reaction is a bit less violent, and it actually creates this brilliantly cool visual. They literally float. Why? Because tiny bubbles of hydrogen gas stick right to their surface like little life jackets. Aluminum, iron, and zinc are much tougher. They won't react to cold or hot water at all, only to hot steam. And lead, copper, silver, and gold, they just sit there. Absolutely no reaction. So the takeaway here is that elements behave very differently based on their reactivity. But guys, you have to beware of the nitric acid trap. Usually, when a metal reacts with an acid, it bubbles and releases hydrogen gas. But nitric acid, or HNO3, is an incredibly strong oxidizing agent. Instead of letting that hydrogen gas escape, it immediately oxidizes it and turns it into water. It's a total trap. There are only two exceptions that still manage to actually release hydrogen gas with very dilute nitric acid: magnesium and manganese. Do not let this trap get you on test day. And speaking of incredibly strong acids, I've got to introduce you to the ultimate acid mixture, aqua regia. Imagine a liquid so ridiculously potent it can completely dissolve solid gold and platinum. It's made of concentrated hydrochloric acid and concentrated nitric acid, mixed in a very precise 3-to-1 ratio. Want a super simple memory trick for this?
The formula for nitric acid, HNO3, already has a 3 in it, right? So the 3 in our ratio just belongs to the other guy, hydrochloric acid. Boom. Easy.
All right, section 3, the ultimate leaderboard.
By now, you're probably wondering, how on earth do we actually keep track of which metal beats which? Well, we figure this out through displacement reactions, and this is exactly what it sounds like. A stronger, highly reactive metal walks right up to a compound, kicks out the weaker, less reactive metal, and takes its place. For example, if you drop an iron nail into a blue copper sulfate solution, the iron just kicks the copper right out, and that blue color starts to fade away. Iron is simply stronger than copper. But how do you actually memorize the ranking of all these metals? Okay, I'm going to give you the ultimate Hindi memory trick used by top students everywhere to instantly lock the reactivity series into their brains forever. Just memorize this one phrase. Kedar, Nath, Gamali, Alu, Zara, Fike, Baka Hai, Kyudhari, Ayaga, Otbidega. Let's decode that real quick. Kedar is K for potassium. Nath is Na for sodium. Ka is Ca for calcium. Mali is Mg for magnesium. Alo is Al for aluminum. Zara is Zn for zinc. Fika is Fe for iron. Paka is Pb for lead. He is H for hydrogen. And then the bottom tier. Cute is Cu for copper. Hari is Hg for mercury. Aiga is Ag for silver. And R is Au for gold. And finally, Pitega is Pt for platinum. So potassium is the absolute king sitting at the top, and platinum is sitting quietly all the way at the bottom. Seriously, just write this trick down at the start of your exam and you will easily solve any displacement question they throw at you. And that brings us to section 4, the perfect match. Let's talk ionic bonds. So, why do elements even react in the first place? What are they all searching for? The answer is stability. Every single element out there is just striving for the ultimate goal, noble gas status. Noble gases, like neon and argon, are completely unbothered. They don't react with anyone because they already have exactly 8 electrons in their outermost shell, a perfect octet. All the other metals and nonmetals are just out there desperately trying to lose or gain electrons to hit that exact magic number, 8. Let's actually break down this atomic matchmaking process step by step with the story of regular table salt, sodium chloride. Step 1. Sodium has 11 electrons, meaning it has one extra super annoying electron hanging out in its outer shell. So it drops it. By losing a negative electron, sodium suddenly becomes a positively charged ion, which we call a cation. Step 2. Chlorine has 17 electrons, meaning it has 7 in its outer shell. It desperately needs just one more to reach 8. So it basically grabs the exact electrons sodium just dropped. Gaining that negative electron turns chlorine into a negatively charged anion. Step 3. We now have a positive sodium and a negative chlorine. Opposites attract. A massive electrostatic force pulls them together, creating a perfectly stable ionic bond, NaCl. And guys, because that electrostatic force pulling them together is so ridiculously strong, ionic compounds develop some amazing superpowers. They are totally solid and incredibly hard to break. They also have very high melting and boiling points. You have to apply massive heat to separate them. They're generally soluble in water, but not in things like kerosene. And here is a major exam point, so listen up. They conduct electricity, but only when they are melted down into a liquid or dissolved in water. If they are just sitting there as a solid, the ions can't move around, so absolutely zero electricity flows. All right, you've mastered the rebels, survived the battlefield, memorized the leaderboard, and made the perfect match. So here is your final exam challenge to see if you've really hacked this chapter. Why are our metal food cans coated with tin instead of zinc? Well, think back to that leaderboard we just learned. Zinc is positioned much higher up on the reactivity series than tin is. If we coated our cans with zinc, it is far more likely to react with the natural acids found in our food, which would be incredibly dangerous for us to eat. Tin is way less reactive, keeping our food perfectly safe. See? Once you understand the rules, the whole world just starts to make perfect sense. Stay curious, remember your rule breakers, and keep hacking science.